Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on Journal Physics 1, we want to talk about temperature and heat, which is the new chapter for us to discuss after all of the things about motion. So now we want to talk about the transfer of energy itself, which is heat in this case. And this is the study of thermodynamics. So, before we jump into today's episode, please consider subscribing as well as liking the video as it means a lot to me. And also, all of the notes will be down in the description below. So, let's just jump into the video. So, the way for us to discuss about temperature is to actually first try to understand the concept of thermodynamic equilibrium. So, So what is thermodynamic equilibrium? So if you have a system in a thermal contact, basically basically the way that you could actually state this is that if if they could actually transfer different kinds of energy between each other but not the matters. For example, if I have a system here and also their system here, they are in contact with each other such that it can exchange thermal properties, it will reach equilibrium once its macroscopic properties are no longer changing. So, once such macroscopic properties include, for example, mass or even the energy, but you could also think of it as temperature itself. So, is that the definition of temperature? Well, it's hard for you to define what the true definition of temperature is. And anyways, we didn't really discuss about thermal contact. So thermal contact is basically heating in one system results in change in the other. So that's the definition of a thermal contact. Results in change in the other. So if I apply some heat into the system, this other object will later experience changes in its microscopic properties, such as its mass, its energy, its temperature, or even its dimensions. So that's the definition of a thermal contact. And if there is something called thermal contact, you could you could also state something to be thermally insulated. So this means that the heating in one system doesn't change microscopic properties. That's basically the definition of a thermally isolated system. So with this, we can actually start to define the very first law of thermodynamics, which is the zeroth law of thermodynamics. So what's the zeroth law? It basically states that two systems have the same temperature if they are in thermal equilibrium. So that's the definition of temperature. So if you have two systems, put them together in a thermal contact, you would have both of the system to have the same temperature. So can you prove it? Not really. This is something that you actually observe. You would observe that if they are in thermodynamic equilibrium, it means that one of the properties will be the same, and this property is temperature. So how do you measure this temperature? The way that you measure temperature is by using a thermometer. which basically utilizes a microscopic property that changes in no sorry that changes with temperature. So there are multiple cases of this. One of them is its volume, and sometimes it could also be pressure or even the volume of a gas. So that's basically the way for you to measure temperature, is to actually measure it with another unit that you could actually observe. So there is something called a constant gas temperature, which basically states that, okay, so the constant gas, this is this is a type of thermometer that has its pressure dependent on the temperature itself. So the pressure is a function of the temperature. And with this, you could define a zero. So in here you could define the zero of temperature, which you call as the absolute zero temperature, which is the absolute zero. So we have lots of different ways to to measure temperature, right? We could use the units of degrees Celsius, degrees Fahrenheit, or even Kelvin. So the way that we'll actually try to measure temperature is we will use kelvins. So 0 Kelvin states that the pressure inside this constant gas thermometer is 0, and the triple point of water is defined to be 273.15 kelvins, which I will later discuss after we already talk about, no, sorry, 273.16 Kelvin is the triple point of water. So we haven't truly discussed about the triple point. So I will later discuss about this property in the next video. But for now, we'll just define it to be something like this. So how do you transform certain units into others? So the way that you actually transform degrees Celsius, no, sorry, kelvins into degrees Celsius is that you just need to subtract it by 273.15. That's the way for you to convert Kelvin into Celsius. And you could do some algebra to get from Celsius to Kelvin. And for Fahrenheit, it is 9 over 5, the temperature of Celsius, plus 32. And that's the definition of the Fahrenheit scale. So there are multiple ways for you to measure temperature. For example, if you use Celsius, it basically measures from the freezing point of water towards the boiling point of water, which goes from 0 to 100. And for Fahrenheit, I believe it has something to do with an with a object, no, sorry, a warm water that's 0 Fahrenheit, and then 100-degree Fahrenheit for a normal human body. I believe it has something like that. So there are multiple different ways for you to measure temperature depending on where you actually come from. But for the use of science, you normally use Kelvin. But sometimes you could also use Celsius or even Fahrenheit, and you just need to convert that into kelvins. So that's about temperature. So what about heat? We have talked about the heating of an object, but we didn't really try to understand what heat truly is. So heat, or you will call as Q, is basically the energy transferred from one object to another due to temperature difference. due to temperature. One object to another due to temperature difference. Temperature diff. So that's the definition of heat. So let's just state if you have a system here, and then there's another system here. This guy has a higher temperature, this one has lower temperature. You could state that basically the heat is going in this direction, heating the other system up. So that's the definition of heat. It is the transfer of energy. So it is not a it is not a energy in which it only exists in one system. Heat is the transferred energy due to temperature. That's the thing that I want you to remember about. So what is the energy that is associated with temperature? That is something which you call as the internal energy or thermal energy. Internal or thermal energy. So this is the energy related to the temperature. So it's the energy as a function of temperature. So a system with high temperature has high thermal energy. That's the way for you to think about it. So that's all about temperature, heat, as well as the thermodynamic equilibrium, which defines all of the rules that we need to use for the future. Let's now talk a little bit about heat capacity as well as specific heat. Heat capacity and specific heat. So what are these? So the best way for me to explain this is to actually just straight away define the formula. So heat capacity, or C, is basically the amount of heat per unit temperature. And the units is joules per Kelvin. So if you actually look at the definition itself, you would know that the Q over the change in temperature would be C. So that's the definition of Q. No, sorry, that's the definition of C, which is something like this, which is normally written. So what is specific heat then? Specific heat, or lowercase c, is basically the heat capacity per unit mass. So looking at the definition again, small c is basically the capital C over small m. So you would know that the Q is mc delta T. So this is the formula that you normally define what heat is. It's basically the transfer of energy in which you already know the certain mass as well as the certain specific heat. So for example, if you have a system changing from 0 Kelvin to 273 Kelvins, you can just plug it in here and you would figure out how much heat is applied towards the system to get that certain amount of thermal energy. So basically thermodynamics is also using the conservation of energy to solve most of its problem as well. So that's something for you to also to remember. And anyways, the unit here is joules per kilogram Kelvin. So talking about the units of heat itself, you could use joules, but normally you would use a unit called calories, or cal for short, which is the heat needed to raise the temperature of water from 14.5 degrees Celsius to 15.5 degrees Celsius. So this is just a definition of the unit itself. So there's a conversion factor going from joule to calories, which is, so 1 calorie is actually 4.184 joules. So that's just some definition of the unit that you use in thermodynamics sometimes. So let's talk about the equilibrium temperature now, because we have already discussed about the definition of heat itself. So if you have two, sorry, so for a, so for the equilibrium temperature, if you have two systems here, each having its own mass, its specific heat, as well as its initial temperature, M2C2T2, and you bring them into contact with each other, something like that. First of all, you need to conserve mass. So the M1 would remain to be M1. Specific heat, let's just assume that to be the same, because we are not transforming the state of matter. And for the other one, M2 and C2 would also be conserved. But they will have a new temperature called the TEQ. So how do you solve for this TEQ? So just by looking at this, you need to conserve energy, right? So the internal energy from the left and the internal energy from the right should be the same. No, sorry, the sum should be the same. But the only difference is that there is a little bit of transfer from here to here, and that's what you call as the heat. So we'll just assume T1 is greater than T2. So just by looking at this, you would know that the heat going out of the first system would be M1C1, the change of the temperature, which is T equilibrium minus T1. And the value here should be negative, and if you notice this is negative, that means energy is going out. Okay, but then this energy should be equal to the one that is going into the system, which should be M2C2, the equilibrium minus T2. So the value of here of this one should be positive. No, sorry. Oh no, sorry, my bad. These two should be positive anyways, because otherwise positive equals to negative, that doesn't make sense. So basically this is the amount that is given and the amount that is received. So, okay, something like that. So you could write this to be M1C1, the change in temperature. Well, technically, well, we'll just bring it here. So this is 1 minus equilibrium. So it's the change of the temperature. So basically this one is the negative. Put that there. It will be a positive. Plus M2C2, the change of temperature, straight away, should equal to 0. That's the only condition that you need to achieve for to obtain the equilibrium temperature. So we have already talked about the equilibrium temperature itself. So let's start to talk more about heat transfer itself. So you might remember from physics that there are 3 different types of heat transfer: conduction, convection, as well as radiation. So there will be only two things that I will discuss much more fully about, while convection is a much more different story. So for conduction, this is the heat transfer through physical contact. And there is a formula for this. Uh, the way that you write this is the heat is the negative Ka times the change in temperature over the change in the position. So if you have, for example, a slab of block and there's a temperature difference, this is T1, this is T2. You could put T1, the T2 minus T1 here. This is the T2 minus T1. And then there will be this will be a surface, right? With the area A. And the change of X, that's basically the width. And the K here is a constant, which you call as the thermal conductivity. Thermal conductivity. So the higher your thermal conductivity, the easier for you to transfer the heat. And why the negative sign? It only tells you in which direction the heat is actually going. So in here, it basically states that the heat is going away from the hotter object. That's the way for you to think about it. And so you could actually convert this thermal conductivity into something which you call as a thermal resistance. And this thermal resistance can be defined to be R, which equals to delta X over Ka. So the units will be flipped a little bit. So you could transform this into the negative change of temperature over R. So this thermal conductivity has units of watts per meter Kelvin, while for the thermal resistance, it has units of kelvins per watt. And anyways, I forgot to mention that H is basically the dq over dt. This is the change in heat over the change of time. The t here should be the time. So you could do the integral to figure out what is the flow rate of the heat. So this is basically the flow rate. This is the flow rate, yeah. And the unit is in watts. So we have talked about the thermal resistance, but sometimes people use another way for you to describe a microscopic property, which you will call that to be the R factor. So that's the way that I will write the R factor. The R factor is defined to be R times A, or basically the delta X over K. So this is a property that only depends on its width and also its thermal conductivity. So if you later layer out multiple of these, you would obtain the thermal resistance. So basically, to figure out the resistance, you just need to divide the R factor over the A, and that will give you the thermal resistance of the object that you have. So this is something that people sometimes use to actually to measure about resistance. So that's about conductivity. Now let's talk about convection. Well, I won't really discuss much about it because this is basically heat transfer from fluid. And we have last time already talked about fluids. It sometimes get very messy, so I won't really discuss much about convection. But for radiation, you could say that radiation is the transfer from electromagnetic wave, which you might have not discussed much about because this will later deal with light itself, which is on general physics too. So the easy way for you to actually to understand this is that every object that has temperature emits heat, and the relation called no sorry and the radiation called P is defined to be E sigma A T to the power 4. So A here is the surface area. The T stands for absolute temperature. So Kelvin is one of such absolute temperature. Sigma is defined to be a constant, and E is 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 the effectiveness. This is effectiveness. So the value of E goes from 0 to 1. That's that is that is that is one of the things that you need to know is that the E here is just effectiveness. It is how dark or how light it is. And a black body, oh sorry, yeah, sorry. Uh this is not called the effectiveness. It is actually called the emissivity. Emissivity, which is basically basically the effectiveness in emitting radiation. And so for a black body, the emissivity is 1. So basically, for a dark object, it is easier for it to actually release heat. And actually, this also means that it is much more easy for it to receive. No, sorry. It is easy for it to receive heat as well. So it is much more like a spring with a very high. No, sorry. The way that you could actually think of this is that for a black body, it doesn't truly hold its heat. It just releases it anytime. But compare that to a white object. It doesn't really want to it doesn't really absorb that easily. It doesn't absorb light that easily, but also it also it also emits heat much more harder. So that's something interesting for you to think about. For example, if you are wearing stuff during a summer day, you might wear a white clothing instead of a black clothing because with a white clothing, you will feel yourself much more cooler compared if you use black clothing. So that's a little bit about the emissivity. So we have already talked about this emissivity. So now let's talk a little bit about the constant itself. What's the value of this constant, sigma? This is the Stefan-Boltzmann constant. And the value is 5.67 times 10 to the power of negative 8 watts per meter squared Kelvin to the power 4. So this basically tries to cancel out all of the units just to make sure that its units is still the same to be watts. So this is a universal constant that never changes. So it is important for you to remember this constant because it could be used in a thermodynamic system. So after we have already talked about all of these types of heat transfers, I want to talk about the thermal energy balance. So let's say if you have an object here to be heated up by radiation, I normally state that to be gamma, but sometimes you could call that to be h nu, which I will not really discuss much because this will deal with a little bit about quantum mechanics, but I would just state this radiation is h nu, and it basically heats this object up with emissivity, let's say 1. And let's also assume that there is there is also an object behind this that is in thermal contact between between the between the black body as well as the block here. So the question is, what's the how much heat is experienced here? Oh, sorry. Yeah, how much heat transfer is experienced at the very end here? So what's the heat transfer here? So this is a very interesting question for you to ask because this deals with the thermal energy balance. So let's just assume that we have already let this out within a very long period of time. So this will later have a certain temperature. So in here it receives P amount of energy from the outside world, which has a certain temperature. And so this will later increase its temperature, and there will be a temperature difference here. So there will be some conduction going on between the black body and the point in which we try to quantify the heat. So just by doing the balance, you would solve for the thermal energy balance. And so anyway, something that I also want to talk about is the surface area itself. So the surface area in here is 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 only the half that is actually experiencing this heat, which is actually pi r squared, if you see from there. But the amount of radiation going outwards is gonna be 4 over 3 pi r cubed, right? That's the area. So solving for the balance itself, there should be a temperature that basically balance out the amount of heat going in and the amount of heat going out, as well as the enthalpy going towards the other end. So I won't truly discuss much about this, but I will leave it up to you for you to actually try to solve this on your own. So that's all for today's video. I hope that this video is helpful for you all. And don't forget, if you like this video, please consider subscribing as well as liking the video. And thank you very much, and I will see you on the next episode.